amplitude. Okay, so amplitude is defined as being the measure to a maximum or a minimum point of a wave kind of thing, given like where the middle is. So the shape of the tangent, since it's no longer like this continuous wave that has consistent maximums and minimums, it doesn't even fit into the realm of like how to define amplitude. So we don't say undefined, we don't say it goes to infinity, we say it has no amplitude. Yeah. Because it cycles through all of its values by the time it gets to pi instead of 2 pi. So now the fourth point on the graph for tangent is going to be pi. Which means what do we scale the parent graph by? What's the first mark on here? What's everything measuring? Pi over 4, okay? So the one thing in common, sine, cosine, and tangent, is that whatever the period is, whether it's the period of the parent function or some sort of horizontal stretch or compression you calculated, that goes on that mark, and when you divide that by 4, you can get what each tick mark value is on your graph, okay? So in this case, it would be pi over 4, okay, which would make the next one 2 pi over 4, which reduces to pi over 2. And then 3 pi over 4, that's like 4 pi over 4. And then you'll see one cycle right there, but we kind of looked at it and saw that it's a little bit hard to tell what's going on. So we continued it a little bit. So 5 pi over 4, and then 6 pi over 4 would be like, okay. Now, what we found out, if you just go through one period of the parent function, we saw it goes 0, then it goes up to its higher point that we mark, and then there was an asymptote right here halfway through. Those are all the undefined values that are giving you those asymptotes. Then here was at its lowest point, and then it was back to 0. So that completed the cycle. Start at 0, go up to 1, undefined, down to -1, back to 0. Okay? Then it would start going through the cycle again. So you can just graph this part each time. But again, what we said is this is difficult because it's hard to tell what's going on here. So what we said is just extend the cycle if you want till one more asymptote so you can kind of see what's going on a little bit better. So if it goes 0, up to 1, asymptote, -1, 0, it would go back up to 1, and then this one would be an asymptote also. Okay. So yes, for this parent function, I'm actually graphing a little bit more than one cycle, like 1.5 cycles, but I'm doing it just more for my peace of mind so I can actually see where things are on the graph. I don't know, for my brain, it's nicer to see like this concrete area right here, but I also want this reference point at 0, so I'm just kind of letting this stuff stick in the graph. So we have this. And then here we have this curve going like this. And then we could continue that pattern. People asked, like, what happens on the other side over here? Well, it continues the pattern it was going. So if this was the higher point we're marking and then 0, the next mark on the graph would mark the lower point that we were marking. Then the next one would be another asymptote, and you would see that same curve. So you basically see what's between these asymptotes right here just repeat itself over and over and over again. Okay, in each direction. So this is like a copy of this part right here, okay? And then you would see that continue the other way. Is this all right with everybody? Okay. So again, you don't have to go this far. You could stop right here. It's nice to have the point at 0, 0 in case there's a horizontal reflection or something like that. You want to reflect things in the right order before you shift them. But it's nice to see between two asymptotes sometimes is a little bit easier than looking at it the other way. Okay, so the period of the tangent graph is pi. That's what the parent function looks like. And it has no amplitude. But you will be asked, so you have to be equipped enough to say none for the graphs that continue up and down. The only graphs that have amplitudes are the ones that are trapped inside a little wave that doesn't extend past a certain maximum and minimum. Okay? All right, so any questions about the parent function? Because now we're going to do, just like we did with sine and cosine, we're going to take this and we're going to stretch, compress it, all that kind of stuff. Yeah. So the asymptotes were the point on our charts where we plugged in a point and the tangent was undefined. Okay? So you basically want to have the parent function eventually memorized. Okay? Just like we do with the sine and cosine. When we go to graph a sine or cosine function, we put those 5 points on the graph. We do our horizontal stretch or compression by rescaling the graph. And then we do all the other transformations. Okay? And we're going to do the same thing here. Okay? but we're just going to start with this picture. It's a little more complicated, right, because of the asymptotes and all that kind of stuff. All right? Any other questions on the parent before we leave it and try to actually do some transformations? All right, so, oops, sorry. Okay, so the problems that I'm picking out are from the end of the investigation that you were working on yesterday. There is not enough room at the bottom of that investigation for you to do all these graphs, especially if the graphs involve like drawing one and then drawing another one once you've like adjusted everything, right? So you'll probably want a separate sheet of paper. This is your homework tonight, so essentially we're doing 3 of the 8 problems you have to do for homework as examples, leaving you with only 5 to try to complete on your own, okay? Yeah. We're going to use all of this. And so we're always going to stretch or compress just by rescaling this part right here horizontally. And then vertically, it's going to be like it was before. These ones on 0 aren't going to move. These ones are just going to get stretched further away from them or closer to them. Yeah. So it would be like if we printed all of it and did all of it. We don't want to do that because it gets confusing, but we do probably want at least this section because without that, it gets a little bit hard to tell, you know? All right. Okay, so looking at the function, what are the transformations that are going to take place? So I have to put the parent function on the graph, and then I have to do what to it? Jordan. Good, I have a vertical stretch by 2. Now, this isn't going to change from the sine and cosine graphs. The ones along the 0 or kind of the middle axis of the graph are going to stay there, and it's the points that were above or below them that are going to get stretched further away from them by that multiplying of 2, okay? What else is going to happen to this graph? Yeah, up 1, okay? So the whole graph is going to move up 1, meaning instead of those middle points being here on the 0 axis, they're going to end up being here where 1 is marked, okay? So think about it as you're planning your graph. As I go to plot my graph, I'm just setting some stuff up on the final graph, but I'm going to go redraw the parent before I actually start because it's new to us. We have to learn it and get used to it, okay? But before I start, I'm just putting this here as a reminder of like, oh, this is going to kind of be the middle ground now, right? And if you want to scale enough up and down area, if this is where the middle points are going to be, normally we plot other points that are like 1 above and 1 below, right? And then the tangent function just kind of shoots off up and down around them. Instead of plotting points 1 above and 1 below, how far are those points going to be away from the middle axis? 2, because of the stretch, right? So knowing that the middle points are going to be here, I'm probably going to want at least 2 marks above that because of the stretch of 2 above, and at least 2 marks below that, which I already have here. Do you get what just like to set up my graph so I have enough space to graph it? Okay? There was a hand over here. Did the question get answered? Okay. All right. That was just me kind of like when you go to draw your graph, how do you want to make sure you have enough space? That's where it is. Okay? Now, period of this tangent function. What's the period of this function going to be? Pi, okay? Why is it pi? Good. Look next to the x. There's no horizontal stretch or compression that's happening. No number is multiplying that x value within the function, which means it's going to have the normal period that the tangent function has, which is why I need to know the basic parent function graph, okay? So I need to know that normally the period is pi. This is going to be very repetitive of what we just did, but I'm doing it because this is how you have to like memorize it and get to know it so that you're able to do all the other ones. And what we knew was this. This was technically 1 period at pi. Okay? Where was the asymptote in that 1 period section of the graph? You have to cheat and look back at your parent function. At pi over 2, it was halfway here, right here. Okay? And then if you remember correctly, okay, the points went from 0 up to 1, so we got like this part of the branch. Then undefined, then -1, and then back to 0. Okay? That was basically 1 period of the graph, but we decided it's kind of hard to see it separate like that, and if it helps us to see it more grouped together, we extend it 2 places to see between 2 asymptotes if that's going to help us. Okay? So all I'm doing right there is what I have memorized. If you're like, oh, how did she know that? I know that because I memorized what my tangent parent function looks like. Okay, so I'm not coming up with something new every time. I have to know the sine, the cosine, and the tangent parent functions. Okay, so once I know this, I'm going to do the things to them that you guys said. We said we're going to vertically stretch by 2 and we're going to shift up 1. But no horizontal stretching, compressing, no reflecting. So I'm pretty sure I can graph most of it that way. I don't need to extend my graph the other way. I know that this points right here are the points that are going to now end up here 1 unit, right? And that these points right here that are normally 1 away from that are now being stretched 2 away from that, okay? So if I want to transfer from this to this, okay, there has been no change in scale because there's no horizontal stretch or compression. So I'm going to scale it just like the parent function. Okay? So all by pi over 4s. And the ones you say, well, that doesn't have a 4 in the denominator, write it as a 4th and then reduce it, and you'll have the same thing that I have up there, okay? All right, the asymptotes are not going to change because the only way the asymptotes are going to change places is if you do what kind of transformations? Horizontal stretches and compressions. What else? Horizontal shifts, okay? Or like a reflection in some way, okay? But it actually, since it's 0 right here, even when you reflect it, they end up in the same place. But only the horizontal changes are going to change where the asymptotes are. Does this graph have any horizontal changes? No, right? So it might be easiest for me to mark the asymptotes first because they're still going to be in these same places because I didn't do any stretching or compressing, shifting left or right. So I'm still going to have this asymptote here, and because I like to extend my parent function for my tangent, I have that asymptote there. Okay? Right? Same as this picture right here. So where did I get it from? I got it from knowing the parent function of the tangent graph. Okay? All right, now, these points right here, it goes 0, then it goes up before it hits that first asymptote. The 0 is no longer at 0. Where are my 0 points going to be now in my new graph? Along 1. That's why I put this little dashed line here to remind me those are like the center points now, right? So this is going to be here. Okay. And instead of the points that are above and below it being 1 above or 1 below that point, what are they going to be now? 2 because of the stretch, right? So rather than coming here and plotting this next point right here, I'm going to stretch it so that it's 2 away from there. So you see that this gets stretched vertically a little bit. Okay? Then between these two asymptotes, it went down, middle, up. Okay? But remember, our middle is now along this dashed line. Okay? It's not on 0 anymore because we shifted everything up 1. And the point that was below and the point that was above, there are no longer 1 point below and 1 point above, because they've been stretched by 2, so now they are 2 spaces below and 2 spaces above. Michael? You don't have to. So if you can do it with that, that's fine. Eventually, like I said, probably starting next week, I'm going to make you guys graph at least 2 periods of the graph. The reason being, like I said, I was getting, even though we discussed at the beginning thoroughly that this continues forever in both directions, the questions I were getting, people were asking in a way that they thought the graph stopped at a certain point, and I want you to understand that's not the case. So once you get a period, I want you to be able to show me that you can continue the pattern of the points. I thought that it would kind of be an automatic, not fair of me to assume, but then the questions I was getting were concerning to me. So for right now, yes, that's fine. You can get 1 period of it that way. So any 1 period of the graph is fine, but in the future, you'll have to do 2. So as long as you can extend the pattern, you're fine. Matt?
How can you get like a horizontal asymptote?
Okay, it's not a horizontal asymptote. It's my own notation, and the reason that I put it there, who can answer his question? Carly. Yeah, so it shifted up to 1. So since all of these graphs are periodic, meaning they repeat themselves, right, after a certain period of time, they all have, like, some place that's kind of the center of the points, and then everything else is around that. And 0 tends to be the center for all the parent functions, but every time we shift up or down, it changes where that is. So a nice way to do that is just mark it on the graph because it makes it a lot easier for you to come and plot without actually having to literally shift everything up 1 or something like that. Ariana? Okay, well, first of all, this isn't a horizontal asymptote. Okay, so this is the same question that Matt just asked. This is here to remind me that I shifted up one and that everything used to be centered around this x-axis, but I shifted everything up one. So this, I remember how I marked this right at the very beginning. It's not an asymptote. It's just showing me kind of where the main axis of my function would be. Not asymptote, but axis. Like everything revolves around this. So like sine and cosine waves, they look like this. They have some sort of central axis that everything revolves around. Tangent graphs generally look like this, right? These vertical ones are asymptotes, but they still have this central axis that everything is kind of symmetrical around, right? You see half of it above and half of it below. So the only reason I marked this here is the +1, so that I could easily go from this to this using these points as these points right here. Is that okay?
Yeah.
Okay, so that's my own notation that I put there. It's not anything indicating an asymptote. Okay? Any other questions about this one? Okay, so let's try another one. Oh, so the period of the function would be pi. We mentioned that, right? And then they're going to ask you, like, what's the amplitude of the function? And you're always going to say none every time it's a tangent function because it continues along those asymptotes. All right, next function. All right, so before we start, because we want to set the graph up properly, okay, we want to pay attention to what are the transformations that are happening, because some of those might be significant in our setup, okay? We already know the horizontal stretches and compressions are a big deal in our setup because they help us scale or put the correct numbers along the axis of our graph. All right, so transformations. Somebody tell me, what kind of transformations are we going to see in this graph? Okay, so a shift up one again, all right? So like I said, I might go like this, right? Okay, but this is not an asymptote, right? This is just me saying everything's now going to be centered around that instead of the x-axis at 0. All right, what other transformations, Sean? Good. Okay, see that negative multiplying the x? That's going to cause a horizontal reflection, and we have to be really careful with our function when that's there, because if we count that as a horizontal reflection, if we really want to accurately see which way we're going to shift, we have to take that one transformation out of the other transformations. In other words, factor it out. So when we factor it out, that plus pi over 2 really becomes a minus pi over 2. And what's that going to signify for us? A shift right pi over 2. Okay? Now, because of the horizontal reflection, think about what that means. We normally build our graph this way just because it's easier for us to deal with the positive scale of the graph. But what's a horizontal reflection going to do to our parent function? Yeah, well, not change the period. But, I mean, I see where you're making the connection, because normally if we multiply by a number there, right, it changes the period. But the negative part doesn't change the period. Only if the number changes from 1 does that change the period. So the period will still be pi. Okay? It's important to note. The period will always start as pi. In the next example, we're going to see one where it changes because we actually do a horizontal stretch or compression. So it'll get adjusted with any horizontal stretch or compression. Just like with sine and cosine, you always started out with a period of 2 pi, but then if a horizontal stretch or compression showed up, that changed the period, and we changed the numbers along the x-axis, right? Okay, we rescaled the graph. So our period is still pi, but what is a horizontal reflection going to do? You'd plot your parent function, and then you'd do what? Flip it horizontally. Yeah, so normally we build a bunch of stuff out here to the right side, but what's really going to happen is it's all going to show up on the left side like it's been flipped over, okay? So I'm going to draw a little sketch over here of my parent function to remind myself what it was like. Pi. And again, where am I getting this from? I have the parent function of the tangent memorized, okay? And you're either going to have to plot those points like you did in the investigation yesterday every time to figure it out, or you're going to memorize it, and then you're going to have the sequence of points that you need, okay? So generally the curves look like that, okay? All right, so what we're going to do is we're going to reflect it, and then we're going to do the other changes that are taking place. So besides our reflection, we then have to shift it to the right, and then we have to move it up 1, okay? So first first we'll reflect it, okay? So I'm going to extend this way. Can't reflect it without some stuff on this side, right? Okay. Yeah, I know. Okay. So normally we number to pi and we go in that direction. I'm going to do all those things we would normally number by, so it would be fourths because we haven't changed the period. We extend it a little bit for those of us that like to see between both asymptotes. But now we want all those negative numbers on this side so we can like see where it ended up and then move it over, right? But luckily you just have to recopy your positive scale but in the negative direction, right? So negative pi over 4, negative pi over 2, etc. Again, how did I know to scale it this way? Because the period didn't change. The period of the tangent function is pi, and I have this memorized, okay? So notice how many times I've said that? Because the main question I'd be getting from people, sine, cosine, and tangent function is, how did you know to start it like that? And I don't have another answer to give unless you want to rebuild the parent function every time or you have the parent function memorized, right? You've got to start somewhere. So just like you guys, that's what I have to do with it. So now what I'm going to do is horizontally reflect all of these points. So this one's going to stay. This one's going to end up on this side, so that branch is going to look more like this, right? And then the asymptote is going to end up next to it, etc. Okay, so this is going to go here. This is going to go up. Here's where this asymptote's going to be. Okay. Do you guys see that reflection from this part right here? Okay. So the next point after the asymptote was down at -1, but I'm reflecting it all the way over here. So this next point will be down at -1. Then this one was at 0. Then this one was at +1. And then an asymptote again. Okay. Now notice I have that red line running through there saying everything's supposed to end up here. Did I do that yet? No, but it's there for me to remember or adjust to or whatever the case may be. Okay? Yeah.
On the test, when we do this, and like we have to shift it to the right,
Mm-hmm.
so do we just do it from like 0 to pi? Like, is that all we have to do? Like that's all
Yeah,
show us.
and then at the end, I'll make sure, you guys need to make sure you have 2 full periods. So I'll show you at the end of the graph what this would look like. We're going to work more on that next week. Right now we're just getting down like with a single pattern of points, how do we shift it and adjust it? And then next week as we practice it some more, we'll make sure we can extend it and follow our pattern. Ariana? I haven't done the +1 yet. Good. Yeah. Oh, sorry. All right. So now we need to shift to the right pi over 2, and we need to go up 1. I can do probably both of those together since I've marked my little up 1 thing and I have an idea of that. Now, how to shift to the right pi over 2? My advice is look at your scale on your graph and decide what pi over 2 means on your graph. So for me, if this is 0 and this is pi over 2, a distance of pi over 2 to me means that much. In other words, 2 marks on my graph represents a distance of pi over 2. So see how I'm using my scale to help me determine how far to go? Okay? So 2 marks on my graph is pi over 2. So basically every point needs to move to the right 2 spaces on my graph. Okay? And they need to move up 1. All right? So I'm just going to start here. This asymptote, 2 spaces. The up 1 doesn't affect the asymptote because it's infinitely up and down. So there we go. This point, okay, needs to move to the right 2, and I'm going to do the up 1 shifting at the same time with everybody. Is that okay? Okay, so I don't have to draw 3 graphs. So it would normally, it's 1 unit above the axis. So it's going to be here. Okay. Then this point, okay, the right 2, and up 1. Okay? It should end up on the axis because it was on the axis before, so that seems good. This point, okay, to the right 2, and it's supposed to be 1 below the axis. So if I took the point itself and moved it to the right 2 and up 1, notice it ends up in the right spot, 1 space below where my new kind of axis is for my function. Okay. Then I hit another asymptote. Okay. Move that over 2 spaces, so it's right here at 0. So I'm going to erase a little bit just so you guys can see better to copy down on yours. So I'm going to take off what was from before. stopped working. Oh, that's mean. All right. So we'll just graph what the final one looks like. Roll with the punches, right? Yeah. It's recording this too, so that's good. Okay. Oh, yeah, I'd like to auto-recover that. Thanks. Too bad you still didn't do what I needed to do here. Okay. That's okay. At least it's all like right now. All right. So what we had at this point, now you guys are going to have to help me. Okay. Well, actually, I can cheat a little bit so I know where we ended up. Okay, so that's where we had shifted everything, right? Thank goodness I know a little bit about the tangent function, right? Okay, so when we go to fill this in, then now you can see, as long as this is what's nice about having the two asymptotes on the graph compared to not having the two asymptotes. So remember Michael's question earlier about if you had to go that little extra bit, you didn't have to. But once I go that extra little bit and I have this part on my graph to move, once I've moved two of the asymptotes into their correct place and I have the points between them, this is the nice part. I can easily fill this in. And now if I had to continue this, if I made you on your test show 3 periods of the graph or 2 periods of the graph, now all you'd have to do is basically be like a little computer and copy paste that to different sides of the graph. So like you see the asymptote here, right? You expect 3 spaces between and then another asymptote. So I could go 1, 2, 3, another asymptote. Okay. You can see which way the curve curves between the asymptotes, and you can copy that idea. So yeah, on your tests and quizzes, I'm going to want to at least see this in the future, okay? Like starting next week, we're going to make sure we include at least 2 periods of the graph. But do you see how if you can really get one of those placed well, you can then just copy it left and right, okay? All right, so the reflection was kind of hard, okay? We just had to make sure we put everything in the right place. Then we moved it to the right pi over 2, which on our graph was 2 tick marks. And we moved it up 1. Okay, and this just helps us keep track of where things are supposed to end up. Okay? So that's our final graph. Okay? Yeah. Okay, so what Megan said was all the transformations are pretty much done with the asymptotes. That's the kind of nice part about the tangent. Even though it's really ugly looking, if you can keep track of where those asymptotes end up, you know that there's going to be some curve between the asymptotes. It's just about which direction it goes, which comes with you reflecting the points right and stuff like that. So normally the tangent function doesn't curve this way, right? It normally curves this way. But we had a horizontal reflection, which makes sense why we're seeing the curves go the opposite direction. Okay? All right. Any questions about what we saw here? So we saw a horizontal reflection, a shift to the right pi over 2, and a shift up 1. Okay, last one that we're going to do together. So this was number 13, and then we're going to do number 15. Yeah, in that case, the period was still pi because there was no horizontal stretch or compression. So this last one that we're going to do together, number 15, this is the only tangent function in our examples we're going to see with a change in the period. Okay? Why is this one going to have a change in the period? Not because the tan has a negative in front of it. Because the horizontal compression because of the 2 that's up there multiplying the x. What is the negative in front of the tangent going to do? Vertical reflection, okay? So at least the transformations didn't change on us, right? If you have to find a silver lining, at least they're all the same transformations we had to do before, just with new crazy-looking graphs. Okay? All right, so I'm going to make I'm going to make a sketch, again, of what the parent function looked like for the tangent. Like I said, maybe not. It's out of batteries, but if I shake it, then the battery hits again, and I'm good. I don't think it was a bad joke. I don't know. I tell math jokes, so I guess I'm not a good judge of that. Okay. Okay. Again, why am I putting this on my paper? This is my starting point for any tangent function. Where am I getting it from? Where am I getting that from? The parent function that I have memorized. That's right. Okay? It's not like someone's whispering it in my ear or something. It's not magic. I learned it, and now I know it, and now I put it on the paper. All right, so we do have a change in period this time, like you guys said, because of that horizontal compression with 2. So normally we look at this function, and our period is what? Pi. We take the period just like we did with the sine and cosine functions and adjust it by whatever the horizontal stretch or compression is, which in this case means to multiply it by 1/2. Always by the reciprocal for the horizontal stretches and compressions, right? Which means the new period is going to be pi over 2. Now, that doesn't mean we're just going to come and cut the graph off and be like, oh, no, that's it. It only goes to pi over 2. What it means is that we're going to change the scale just like we did before, right? That we still want the period to be pi, so we still need to start here and end here. Okay? But this is no longer going to be labeled pi. This is now going to be labeled pi over 2. Okay? Pi over 2 divided by 4 is not pi over 4, so that's going to change the entire scale of the graph. Pi over 2 divided by 4 is going to be pi over 8, which means my graph needs to be labeled by 8ths. Okay? And then I've taken care of the horizontal compression in this case. Yes. Mm-hmm. Because horizontal stretches and compressions work the opposite way you think. So when it's a number greater than 1 horizontally, it's actually a compression, so you always multiply in those cases by the reciprocal. All right, so I'm going to change all these numbers right here. I'm going to number it by 8ths. You should do the same. All right, so we have 1/8, 2/8, 3/8, 4/8, 5/8, and 6/8. Okay. So I didn't change the way it looked. I just changed the scale. I have technically changed the way it looked. I technically took it and went like this, where all of it's happening in a shorter amount of time. But to show that, I just changed the time instead of squishing the graph. Okay? 3 pi over 4. Because it would be like 6 pi over 8. Okay, so that's taking care of the 2. That part's already done. All right? So now, what are the other transformations that have to take place? Okay, a vertical reflection, and what else? A shift down 3. That means instead of my 0 points being across at 0, they're going to be across at -3. Okay? So I'm going to want to put some more marks on my graph here, okay? Because this is where I now expect those points to be. Okay? Again, that's not there because it's an asymptote. It's there to remind me everything is getting shifted down 3. So all these points that I see right here along the 0 axis are now going to be down at -3. Okay? So if I just took this whole graph now and copied it with those 0 points here and things one above it and one below it, I'd have the -3 part, the -3 part. The negative part, what's the vertical reflection going to make the graph look, how's it going to make the graph look different? What's that? What? It's going to be +3. No, we can't distribute it over to there. Are you talking about like distributing the negative? Oh, like when we flip it over? Yeah, but we would flip it before we shift it. So remember with our horizontal, we saw it most with our horizontal. We couldn't shift and then flip, or we ended up in the wrong space. We always had to do a reflection before we did shifting, okay? So this is not going to change to +3. You're not going to flip this over. What you're going to do is you're going to flip these points over here. So these ones are going to, like, if we could take the tangent graph and spin it around the axis, right? This one would go down and this one would go up. So it would go more like this, okay? That's the reflection. Then you're going to move everything down 3. So all your 0 points should still end up here no matter what, okay? So to do that with the reflection, the one thing that's not going to change are going to be my vertical asymptotes right now. So I'm going to go ahead and put those in first. Is that okay with everybody since they're not changing? Okay. So These are numbered by eighths. You have the scale right there. The second one is an asymptote. Okay. And then there's 3 between, and then the next asymptote. Okay. The points along the axis are not affected by vertical reflections because they're on the point that you're reflecting around. So they can't go from above to below because they're right on the axis. So these points are going to stay on the axis, but the axis is no longer going to be at 0. The axis is going to be at -3. So this point right here that's on the axis, it's going to stay at the axis, but the axis is now at -3. Okay. This point that was on the axis, right directly between the two asymptotes, it's going to stay on the axis too, but the axis is at -3. So it's here. Is that okay with everybody that I just did those points yet? Okay. That's because I'm going to do the reflection at the same time as when I'm doing this. Okay. So this point that I want to fill in right here used to be 1 unit above where my axis point was. So it would be right here. Okay. But if I reflect that, it's going to be on the other side of where my axis is, here, going like this. Okay. In between the asymptotes, the points used to go below, on the axis, above the axis, right? We filled in the curve. But with a reflection, those points are going to go above on the axis and then below. So the points used to look like this. This one was here, and then this one would be here. Okay? But then when we reflect those, this one that was down here goes up here. The one that would have been up here goes down here. And then we have this in between like this. Okay? Once you have that set of points between two asymptotes, you could then continue that pattern forever to the left or to the right. Okay? So we took care of the horizontal compression just by rescaling our graph. I'm filling in the same scale that's over there. Okay. So we rescaled our graph. That took care of the horizontal compression. Okay. We moved everything down 3. That took care of the -3 at the end. And points that were below the axis ended up above, and points that were normally above ended up below. That took care of the vertical reflection. Notice that with the tangent graph, the vertical reflection and the horizontal reflection kind of look the same. Okay. Because what they do is they essentially just make the curve appear to be traveling in the other direction than how we saw it before. Okay? All right, so hopefully I tried to pick examples where you guys could see a little bit of everything. So we saw some shifting, we saw horizontal and vertical reflections, we saw how to change the period, okay? So we saw all of that different stuff, so you should be able to each time try to do that. If you have to take more steps, okay? Always start with your parent function and adjust your scale first. Do reflections before you do shifting if you're uncertain of how to do each one together, okay? Any questions?